Welcome back for another deep dive. This time, we're going to delve into the world of Wolfgang Ketterle,
Oh, yes.
a physicist who accomplished something really remarkable.
Yeah.
Creating a state of matter that almost seems like it's straight out of science fiction.
It really does. And to help us navigate through all of this, we have a fantastic essay
Okay.
by Jurgo Schneepat
Okay.
titled Wolfgang Ketterle, Pioneer of the Bose-Einstein Condensate.
So let's break this down a little bit.
Sure.
A Bose-Einstein Condensate, or BEC.
BEC.
What are we talking about here?
Well, imagine cooling atoms down to temperatures so low that they're barely moving.
Okay.
We're talking billionths of a degree above absolute zero.
Wow.
At this point, the atoms start behaving in ways that just defy our everyday experience.
Yeah.
They lose their individual identities and merge into a single quantum entity,
Right.
the BDC.
So instead of acting like tiny little billiard balls bouncing around,
Yeah.
they become more like these overlapping waves,
Yes,
forming one giant superatom?
precisely. And it's a really mind-boggling concept that was first theorized back in the 1920s
Right.
by Satyendranath Bose and Albert Einstein.
Okay.
But it wasn't until the 1990s that the technology existed to actually create one.
So that's where Wolfgang Ketterle comes in.
Exactly.
Schneepat tells us in this essay
Yes.
that he was actually born in Heidelberg, Germany
It was.
in 1957
Uh-huh.
and always had a fascination with science.
Always a strong interest in science, yeah.
So it seems like he was destined to end up
Yeah,
on this cutting edge of physics.
absolutely. And Schneepat highlights his incredible journey through the academic world.
Right.
He studied physics at the University of Heidelberg
Okay.
and later at the Technical University of Munich.
So really going straight for it.
Yeah, going straight for it.
And then his doctoral work was under Herbert Walther,
Oh, yes.
who was a pioneer in quantum optics and laser technology.
A real pioneer, absolutely.
I mean, talk about learning from the best.
Exactly. Learning from the best.
And all of those skills really helped him in his later breakthroughs.
Oh, they prove crucial. Yeah.
Then, in 1990, he makes this move to MIT,
Yes. A pivotal move.
which is one of the world's leading centers for quantum research.
Absolutely.
And that's where his journey into the world of BECs really takes off.
It really does.
So he's surrounded by all these brilliant minds
Yeah.
at the forefront of this brand new field.
Yeah.
But what was so groundbreaking about his work with BECs, other scientists had already created them, right?
You were right.
Like this isn't...
Yeah, Eric Cornell and Carl Wieman created the first BECs in 1995,
Okay.
which earned them a share of the 2001 Nobel Prize in Physics.
Okay.
However, Ketterle's work at MIT pushed the boundaries even further.
And Schneepat really hits on this point.
Yeah,
Ketterle didn't just create a BEC.
right.
He created one with millions of atoms.
Millions. That was key.
Wow.
Think of it like this. Having millions of atoms in a BEC
Okay.
is like having a much larger lens to observe these strange quantum effects. It opened up a whole new realm of possibilities for experimentation.
So it wasn't just about creating the BEC.
No.
It was about creating one big enough
Yes.
to really study it and unlock its secrets.
Yes, unlock those secrets.
What kind of experiments did this allow Ketterle to conduct?
Well, one of the most fascinating experiments
Okay.
that Schneepat describes involves interfering two separate BECs.
Interfering,
Yeah.
like two waves crashing into each other.
Exactly. Imagine two ripples on a pond meeting and creating a new complex pattern.
Oh, okay.
Ketterle did something similar with BECs.
Wow.
And the resulting interference pattern provided undeniable proof
Okay.
that the atoms within a BEC act like waves.
Oh, wow. So this is further confirmation of the wave-particle duality. This mind-bending concept
Yeah.
that matter can act like both particles and waves.
Yes.
Which is like this fundamental principle of quantum mechanics.
Absolutely fundamental.
Okay.
But Ketterle's groundbreaking work didn't stop there.
It didn't.
No. He also used his BECs to demonstrate another bizarre quantum phenomenon. Superfluidity.
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 Okay. You have my attention.
All right.
Tell me more.
In the simplest terms, superfluidity means a fluid can flow without any resistance whatsoever.
Okay.
Imagine a liquid that moves without any friction,
Okay.
gliding effortlessly through any channel or container.
That sounds impossible.
It does. It defies our everyday experience.
Yeah.
But it's exactly what we'd expect to see in a system governed by the strange rules of quantum mechanics.
Okay.
And Ketterle was able to prove that BECs exhibit this incredible property.
So he created this tiny little quantum playground.
He did.
Where the impossible becomes possible.
That's a great way to put it.
Wow.
And his exploration of BECs didn't stop there.
It didn't.
No.
Wow.
Schneppat goes on to detail how Ketterle continued to push the boundaries, what was possible with these ultra-cold systems, venturing into areas like atom interferometry, and even quantum computing.
This is incredible.
It is.
So we've got atoms acting like waves, flowing without resistance, and who knows what else.
Yeah.
It seems like Ketterle opened up a Pandora's box
He did.
of quantum weirdness, and Schneppat has given us this front row seat to it all.
He has, and remember, we're still just scratching the surface of Ketterle's work after winning the Nobel Prize.
Wow.
This is clearly a deep dive that needs more exploration.
Yeah, I think so.
Let's continue.
Let's dive back in. Okay, so let's jump back into the world of Wolfgang Ketterle.
All right.
And these mind-bending BECs.
Okay.
So he wins the Nobel Prize in 2001.
Yes.
What does he do?
Yeah.
He just keeps pushing forward.
He does. He's not content to rest on his laurels.
Right.
Schneppat details how he continued to explore the potential of BECs, branching out into fascinating areas like atom interferometry.
Now, we touched on this a bit earlier.
We did.
But I'm still a little fuzzy on what atom interferometry actually is.
Yeah.
It sounds really complex.
It might sound complex, but the concept is actually pretty elegant.
Yeah.
Remember how Ketterle used those interfering BECs to demonstrate their wave-like properties?
I do, yeah.
Atom interferometry takes that concept a step further.
Okay. And how did he create those interference patterns again?
So he made two separate BECs overlap.
Okay.
And just like ripples on a pond.
Okay.
They created a distinct pattern where they intersected.
Okay.
This proved that the atoms within a BEC act like waves, not just particles.
Right, because of that whole wave-particle duality.
Exactly.
Okay, so how does this connect to atom interferometry?
Well, in atom interferometry,
you
use these interference patterns to make incredibly precise measurements.
Yeah.
Think of it like using the interference of light waves to make measurements in a regular interferometer.
Okay.
But instead of light, you're using matter waves.
Matter waves, those BECs.
Those BECs, exactly.
Wow, so instead of a beam of light, it's like a beam of ultra-cold atoms. That's crazy. What kind of things can you even measure with that?
Well, Schneppat explains how Ketterle's team at MIT used atom interferometry to measure things like gravity, acceleration, and even rotation with incredible precision.
Hold on, are you telling me they created an atomic-level ruler?
It's not a ruler in the traditional sense, but you're getting the idea.
Yeah.
They could detect minute variations in these forces, variations that would be impossible to measure with conventional instruments.
That's remarkable. But what's the practical use of these really precise measurements?
Right.
Like, why go to all that trouble?
Well, imagine the possibilities.
Okay.
Schneppat hints at some incredible applications.
Like what?
For example, more accurate and reliable navigation systems.
Okay.
Ones that are immune to interference or disruptions.
Oh, wow.
Or even instruments that could detect subtle changes in the Earth's gravitational field.
Okay.
Helping us understand things like earthquakes or volcanic activity.
That's amazing. It's like we're peering into a world of possibilities that we've never even considered before.
Possibilities we never even thought of.
But Schneppat says Ketterle didn't stop at atom interferometry.
He did.
He also went into the realm of quantum optics.
He did. And this is where things get even more interesting.
Yeah.
Quantum optics is all about the interaction of light with matter.
Okay.
Specifically at the quantum level.
Okay, I think I'm following.
All right.
So he was basically trying to figure out how light interacts with these ultra-cold atoms in a BEC.
Precisely. And it's not just about understanding the interaction itself.
Okay.
It's about controlling and manipulating those interactions to create new technologies and possibilities.
So in a way, he was trying to use light to control these strange quantum states of matter.
Exactly. Schneppat points out that Ketterle's research in quantum optics wasn't just about controlling single atoms, though.
Oh, okay.
He was interested in creating and studying quantum correlations.
Okay.
Even entanglement.
Entanglement.
Between groups of atoms.
Now, that's a word that sends shivers down my spine.
I know, right?
It's like the ultimate spooky action at a distance.
It is. Entanglement is one of the most mind-boggling phenomena in quantum mechanics.
Okay.
It's this idea that two particles can become linked in a way that even if you separate them by vast distances, what you do to one instantly affects the other.
Okay. That's officially blowing my mind.
Yeah.
But why was Ketterle so fascinated by entanglement?
Right.
What's the big deal?
Well, entanglement is seen as a key resource for a whole range of future quantum technologies.
Okay.
Like super secure communication networks.
Wow.
Or even those ultra-powerful quantum computers we keep hearing about.
Wait a minute. Quantum computers? Is that where this is all heading?
You're right on track.
Okay.
Ketterle's work with BECs actually laid some crucial groundwork for the development of quantum computers.
Really?
Yeah. Remember how we talked about his research on atom trapping?
I do, yeah.
Well, that technology became essential for building the first quantum computers.
Oh, I see. So you need to trap and control individual atoms with incredible precision.
Yes.
To make those qubits.
That's qubits, exactly.
Those quantum bits of information.
Yeah.
And BECs, with their ultra-cold, well-behaved atoms, provide the perfect platform for building those early quantum systems.
They do. Schneppat even mentions that Ketterle was exploring the use of what are called atom lattices.
Atom lattices?
Where atoms are arranged in a grid-like pattern.
Okay.
Each acting as a tiny qubit.
So instead of bits, which are either 0 or 1, we have these qubits that can be in a superposition.
Yes.
Existing in both states simultaneously.
Exactly. And that's what gives quantum computers their incredible power.
Wow. Of course, building a practical large-scale quantum computer is still a huge challenge.
Huge challenge.
But Ketterle's work with ultra-cold atoms was a stepping stone in that direction.
It was a stepping stone, absolutely.
And Schneppat really does a good job.
He does.
Of highlighting these connections.
All these threads are connected.
So we've gone from creating BECs to incredibly precise measurements, manipulating matter with light, and even dabbling in the world of quantum computing.
We have.
It's amazing how all these threads are connected. And it all stems from that initial breakthrough with BECs.
It all goes back to that.
It's like this incredible scientific tapestry.
It is a tapestry.
Woven together by Ketterle and his team.
Absolutely. And remember, this is all still building upon his Nobel Prize-winning work.
Right.
Ketterle's career is a testament to the power of relentless scientific curiosity.
It makes you wonder what else is out there waiting to be discovered.
It does.
What other seemingly impossible things might become possible in the future?
That's a great question to ponder.
Yeah.
But before we get too carried away, I think it's important to take a step back and consider the bigger picture.
Right.
What do you think is the most significant aspect of Ketterle's legacy?
Okay.
What stands out to you most from Schneppat's account?
You know what really strikes me is how Ketterle has really pushed the boundaries of what we thought was possible.
Yeah.
It's not just about, creating a BEC.
Right.
It's about using that to really launch into all of these other mind-blowing concepts.
Yeah.
Like superfluidity, atom interferometry, and even quantum computing.
It's incredible. And Schneppat really highlights that
He does.
He doesn't just focus on the discoveries themselves, but how Ketterle's work has opened up all these new avenues of research.
Right, and they go way beyond the lab.
Beyond.
And it's not just his own research.
Sure.
Schneppat really emphasizes how Ketterle has really fostered this whole new generation of scientists.
He has. His lab at MIT has become this breeding ground for top quantum researchers.
It's like he's created a Ketterle School of Quantum Physics.
I like that.
With all his students carrying the torch and making all these other incredible contributions.
Yeah, passing on that knowledge and that inspiration.
It's pretty remarkable.
It is.
Well, he certainly sparked our curiosity today.
He has.
Schneppat's essay has given us so much to think about.
A lot to think about.
It's amazing to consider the potential real-world applications of this research that seems so esoteric.
It is. From those ultra-precise sensors that could revolutionize navigation and Earth monitoring, to the potential of quantum computing to change fields like medicine and material science.
Yeah.
It's really vast.
The possibilities are huge.
They are.
But, with any powerful technology, there's always these questions.
Of course.
What are the ethical implications?
Yeah.
How do we ensure that these advancements really benefit society as a whole?
Important questions. And while Schneppat doesn't go too deep into them, he does mention that broader societal impact.
Right.
It's clear that Ketterle's work isn't just about advancing our understanding of the universe, it's really about shaping the future.
It is.
And it makes you realize that we're living in this time of incredible scientific discovery.
Yeah. Where the impossible is becoming possible.
Yeah. And it all started with this really simple question.
Yeah.
What happens when you cool atoms down to almost absolute zero?
It's amazing, right?
I think that's the beauty of Ketterle's story, as told by Schneeberg.
I agree.
It highlights the power of curiosity-driven research. Right. The idea that even the most fundamental discoveries can have these really profound and far-reaching consequences.
Absolutely. It's not always about the end goal.
Right.
Sometimes it's about the journey, the exploration.
Exactly. Ketterle wasn't setting out to, build a quantum computer or create an ultra-precise gravity sensor.
Right.
He was just driven by this desire to understand the fundamental nature of reality.
The curiosity.
And that's what makes his story so inspiring.
It really is.
It's a testament to the transformative power of human ingenuity and the endless possibilities that exist at the intersection of science and imagination.
I love that.
Well, I don't know about you, but I'm feeling really energized after this deep dive.
You too. Schneeberg's essay has given us this incredible glimpse into the world of Wolfgang Ketterle.
Yeah.
And the legacy that he's building.
It is quite a legacy.
And it really leaves us with this sense of wonder.
It does.
About what the future holds for this really exciting field.
A lot of excitement out there.
Yeah. There's so much more to discover, so many questions to ask, and who knows what amazing breakthroughs are ahead.
Yeah. And maybe one of our listeners will be inspired to make that next great discovery.
To make that next breakthrough.
Exactly. In the world of quantum physics.
So we'll leave you with this thought.
Okay.
If atoms can behave like waves,
flow
without resistance, and become entangled across vast distances,
right,
what other impossible things might be possible in the quantum world?
That's the question, isn't it?
What wonders await us as we keep pushing the boundaries?
It's exciting to think about.
Of what we know.
It is. Keep exploring, keep questioning.
Yeah.
And we'll catch you on our next deep dive.
Until then.